In parts 9 and 10 of this series, I focused on the crucibles and flux material. I also mentioned special techniques. In this presentation, I will be focusing on some of the special techniques that are used for the digestion of hard-to-decompose and refractory samples, some of which a small-scale miner, prospector, or hobbyist will not use, but may send the samples to a lab that may use some of these processes. Others may try to experiment with some of these techniques, some of which I do not recommend due to safety concerns, although YouTube and Google has plenty of resource material that may be accessed for experimentation. Some other techniques, such as sintering, may be used extensively, depending on what you are trying to achieve. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. As some materials will not fully digest by acid digestion alone in an open vessel, a bomb is employed for this reason. These are pressure vessels that withstand strong mineral acids and alkaline solutions. These are designed to operate under higher temperatures and higher pressures, some up to 3,500 degrees psi. Special heaters are incorporated with par bombs. However, an oven may be used if temperatures do not exceed 500 degrees centigrade. Being closed system digestion vessels, there is no loss of analyte. There is no contamination from cross-sample contamination probabilities. Inorganic material will dissolve quickly with hydrofluoric, nitric, hydrofluoric, and sulfuric acids using bomb procedures. The stainless steel containers that are lined with a Teflon coating not only resist cross-contamination between samples, they also resist the effects of hydrofluoric acid. Caution must be taken with these digestion vessels. They are never to be completely filled due to the high pressures. There must be a vapor space between the material and the lid of the container. Excessive pressure will cause expansion of vapors and must be considered as there exists an explosion hazard. Therefore, the maximum fill is 2/3 of the container's volume. In addition to, perchloric acid is never used with these vessels due to its excessive reactivity with organic material and oxidizing power. PTFE stands for polytrifluoroethylene, better referred to as Teflon. Teflon is not only used in par bombs. These also come as open system reaction vessels, or better stated, as low temperature crucibles. These low temperature crucibles can be used in an oven or microwave oven. More on microwave digestion in an upcoming slide. Now these are used for soil samples containing mixed silicates. Approximately 150 milligrams a sample would usually be weighed out, and 4 milliliters of hydrofluoric acid along with 0.3 milliliters of aqua regia is added. The container can be either a Teflon bomb or a Teflon crucible, which is heated to 105 degrees centigrade for 30 minutes until fully decomposed. A bomb would be more suitable for this application. For samples of ilmenite or chromite, a steel bomb with a Teflon liner would be more appropriate. 0.5 grams of material would be weighed out. Added would be a mixture of sulfuric acid and 48% hydrofluoric acid, having a solution ratio of 1:1. It is then heated to 240 degrees centigrade for 3 to 4 hours. Now, using par bombs, minerals are attacked under high pressures and high temperatures. But anytime sodium peroxide is involved in the decomposition of material, the working temperature is 500 degrees centigrade with a stainless steel bomb. Par bombs with Teflon liners, the working temperature is lowered. Working temperatures will range between 105 and 250 degrees centigrade. Precautions, as previously stated, must be considered using sodium peroxide at 500 degrees centigrade. Teflon decomposes at 300 degrees centigrade. Therefore, working temperatures with Teflon must not exceed 250 degrees centigrade. The first on my list of special methods, which some may wish to experiment with, is decomposition by chlorination. The diagram shows a quartz cylinder, a couple of heat-resistant stoppers with glass tubing at each end. The porcelain boat which contains a sample is placed inside the tube prior to the end cap being installed. The rest should be self-explanatory. The outlet may be attached to a water bath or condenser in order to capture any volatilized analyte for further analysis. This procedure should be conducted with a fume hood or in a well-ventilated area, preferably outdoors, due to the toxic chlorine gas that is used for a desirable reaction to take place. The tube is heated to 250 to 300 degrees centigrade, and the chlorine gas is slowly passed through the tube. The gas reacts with the sample components during roasting, which will become volatilized and therefore selectively separated from the sample. After the chlorination process is completed, the residue, being ash, is leached or decomposed by acid. The resulting analyte in solution may be copper, chromium, nickel, and/or even cobalt. If the water bath or some distilling apparatus was added to the outlet, iron, sulfur, phosphorus, germanium, and/or gallium may be recovered. However, feldspar, olivine, pyroxene, apatite, magnetite, and even chromite will not be attacked by this method, and therefore be left in the boat as additional residue. The upside is that the metals and metal sulfides may be separated from the silicates, such as siderites, which are iron 3 carbonates. Now these will lack sulfur and phosphates. Microwave technology is relatively new and is evolving. This type of heating accelerates chemical decomposition reactions. It is faster, cleaner, more accurate, and results are reproducible. This technology uses electromagnetic radiation at 2450 MHz. The earliest versions used closed-system Teflon containers based on the bomb digestion methods and theories, which allowed for complete digestion of sample material. Microwave heating reduces the thermal stress on the Teflon vessels, which in turn allows for higher temperature of 280 degrees centigrade without damaging the vessels, instead of the 250 degrees centigrade maximum as applied to bomb requirements. These units, like your home microwave oven, have rotating turntables that ensure a homogenized distribution of microwave radiation, which eliminates hotspots, resulting in even heating throughout the chamber. The Teflon vessels operate at a pressure of 110 psi and incorporate pressure relief valves to overcome overpressurization. Computerized control is incorporated to keep timing, temperature, and plate rotation stable and consistent for maximum efficiency and safety. Mixtures of hydrofluoric, hydrochloric, and nitric acids may be used. However, perchloric acid, due to its explosive nature, is not. Newer units are now focusing on open vessel, low pressure closed vessel, as well as high pressure closed vessel digestion. Some newer models also incorporate ultrasound technology to enhance chemical decomposition reactions. Microwave digestion has its advantages. The biggest is that it will reduce digestion time up to 80%. Higher temperatures are achieved in comparison to hot plate heating. Rapid energy transfer allows for a more even heating all the way around. Evaporation losses are kept to a minimum, or none at all. Due to the efficiency, small amounts of reagents are needed. This reduces reagent cost. Loss of volatilized analyte is also kept to a minimum. In addition to, sample preparation time is reduced. The system is easy to operate due to its automated features. The decomposition of refractory and hard to decompose material is easily and efficiently decomposed. It is not sample matrix dependent. The unit is fully computerized to control temperature, decomposition timing, and plate rotation for even heating. The instant on-off switch results in rapid heating due to the instant distribution of electromagnetic radiation. Now, there are also disadvantages, and the first is the high cost of purchasing one of these units. These are not cheap. Then there is the cost of maintenance. The small heating chambers will not allow for large batches of samples. In other words, no volume sample preparation is achieved. It is also new technology, new technique, and may require some experimentation with your sample material to obtain maximum results. I must include a warning. Do not use a domestic home or commercial microwave that is used for cooking. These are not designed for the decomposition of sample material. Temperature cannot be monitored or controlled. Turntables have only one rotational speed and are not controlled for efficiency. Vessels that are heated are under high pressure and may explode. This becomes a major health and safety hazard. Sintering can be achieved by the use of a Bunsen burner, a muffle furnace, or a special sintering furnace as shown. There are a lot of different types of sintering furnaces. In sintering, samples are heated to a temperature that is just below the fusion temperature of the sample. This avoids any corrosion of crucible walls and avoids volatilization of analyte at times. The completeness of the decomposition fully depends on the reagent used in the process, as well as the temperature used and the duration time for the reaction to be fully completed. Commonly used is sodium peroxide for the determination and analysis of rare earth elements. That is, rare earth elements having atomic numbers in the periodic table ranging from 57 to 70, being lanthanum to ytterbium, are made soluble using a sodium peroxide sinter method. The residue is leached with distilled water, then acidified with nitric acid. Sintering may also be used for the destruction of organic material. For some samples, organic material is considered as undesirable contamination, others as material containing analyte of interest. In all cases, organic material must be decomposed, and there are three methods by which this can be done. The first and the least reliable is dry ashing. This is when the sample is usually soil samples are placed into a crucible and ignited, that is, burned by a torch. The ash, being the remaining residue, is then dissolved in acid, converting the elements of interest into ions in solution for the subsequent analysis. The drawback to this method is that some material may be lost as dust, while other elements lost by volatilization. Now, loss may be reduced using a muffle furnace, where loss created by the force of a torch is eliminated, resulting only in loss by volatilization. The process for wet oxidation starts by dissolving the sample in acid, while heating the solution until all vapor ceases to be expelled. The organic compounds are decomposed, resulting in the release of carbon dioxide gas, and a solution containing the ions of the remaining metallic salts. Additional volatile elements may be lost due to the open system. That is, the decomposition is done using a beaker that is open to the environment. In this method, the solution can be analyzed for analyte of interest, as well as concentrations. Any residual may be filtered for further analysis. The use of a closed system and a condenser or a series of simple gas traps may recover any volatilized analyte for further separation and concentration analysis as shown in this simple setup. Pyrolysis is just a form of dry oxidation, similar to dry ashing. The pulverized sample is mixed with a flux to aid in decomposition and subsequent ashing of the organic material. However, using a furnace such as a muffle furnace is shown, volatilized elements will be lost. The resulting ash, containing the residual elements, may now be digested by an open system method, and the remaining residue filtered for further analysis, or by total decomposition using a bomb, a microwave method, or by a multi-acid digestion. Now there are other methods that may be devised, where the volatilized elements may be captured, either by using a condenser or by a series of water traps, sometimes referred to as water baths. This method is said to be most reliable, however, it is still being discussed in the scientific community. Pyrolysis, wet ashing, and dry ashing is a common procedure, as well as being an easy application for sample preparation, especially for the small-scale miner, prospector, and hobbyist. Organic reagents are often used in chemical analysis. Organic chemistry is a chemistry science all on its own, and quite complex, however. I mention it now and will not go into a lot of theory. I mention it now as some of these reagents will be discussed in upcoming presentations in the series. These are carbon-based compounds, made of carbon chains or rings, containing mostly hydrogen. However, other non-metallic, as well as metallic elements may exist within these compounds. These are used as precipitating agents, coloring agents such as in spot tests, and titrants, which will be discussed during the presentations on titration. Other uses are separatory solutions based on densities. Concentrators are agents that will solubilize a compound, leaving others insoluble with the compound in solution. Concentrators and separatory solutions go hand in hand. This is where one element will be decomposed into one solution while the rest will decompose into another. Now both solutions having different densities will float on top of each other. The two solutions and their analytes can then be separated using a separatory funnel for analysis of both solutions. Masking agents are used to mask or isolate interfering or undesirable elements. The most often used organic reagents are acid-base indicators, which are utilized for titration endpoints. More on these will be discussed in future presentations, focusing on titration methods for quantitative analysis. This table shows the most common organic acid-base indicators used for titrations. Now, titrations will be discussed in future presentations. For now, it's enough to say that these compounds will change color within the given pH range of a solution. The point where the color changes and is stable is known as the endpoint. This table will be invaluable later on in this series, and I urge you to stop the video and take a copy of this table as a reference going forward. Well, this concludes part 11 of the series titled Classical Chemical Assay for Small-Scale Miners, Prospectors, and Hobbyists. I discussed some of the special techniques, that is, methods used for the preparation of sample material, meaning the total decomposition of your samples. In addition, I introduced some of the aspects in regards to organic reagents and their uses. Not all of those special methods would be used by small-scale miners, prospectors, or hobbyists, and has been presented for information as to what may be conducted in a geochemical laboratory for instrumental sample preparation and subsequent analysis. Now, I hope this presentation entices you to view Part 12 when it is published. If you found this presentation interesting or helpful, or if you know of someone who may benefit from this presentation, please give it a like and a share. It's my only reward. I am Rob Boyko, Boyko Mineral Exploration, and I thank you for watching.